You know what a compass is. Of course you do. It sits in your hand like a small, quiet promise, a circle of glass, a needle that trembles, then stills. A letter N printed in bold red certainty. You've seen it in films. The explorer holds it up, the needle swings, and suddenly everything makes sense. Direction is restored. The hero knows where to go. You've held one yourself, perhaps. At school, on a camping trip, in a scout hall that smelled of damp wood and old socks. Someone showed you how to hold it level, how to let the needle settle, how to trust the small red arrow that always pointed the same way. And you thought, yes, I understand this. You thought, this is simple. A magnet. The Earth. North. Simple. But here is the thing about simple objects. They are never, ever simple. The compass you are imagining right now, the one that feels so familiar, so ordinary, so utterly known, is one of the strangest objects that has ever existed on this planet. It does not point north because of a rule. It does not point north because someone decided it should. It points north because the entire planet Earth is, in a very real and scientific sense, a magnet, a slow, breathing, ancient, shifting magnet that has been quietly humming its invisible song for 4.5 billion years. And the needle hears it. The needle has always heard it. Long before there was a compass to hold it. Long before there was a human hand to hold the compass. Before there were ships or explorers or scout halls or films, the invisible force was already there, pulling, whispering, organizing the world. So let us sit with that for a moment. Let us not rush past it. Let us not treat the compass as a tool we already understand. Let us treat it instead as what it truly is, a window. Beneath your feet, right now, something impossible is happening. Not metaphorically, not poetically, scientifically. At the center of the Earth, roughly 5,100 kilometers below where you are sitting, beneath layer upon layer of rock and heat and pressure so enormous it defies imagination, there is a ball of solid iron roughly the size of the moon. And surrounding that solid iron ball, like a vast, slow-moving ocean of liquid metal, is an outer core of molten iron and nickel, swirling in currents driven by heat so intense that the rock around it would become gas if exposed to open air. This swirling, this endless, ancient, slow swirling. This is what your compass is listening to. Every time you pull a compass from your pocket and watch the needle settle, you are witnessing a communication between a small sliver of magnetized metal and the churning liquid heart of the planet. Think about that. Really think about it. You are not measuring distance. You are not reading a map. You are receiving a message from the core of the Earth itself. A message that has been broadcasting, without interruption, without pause, since before the first fish swam in the first ocean. The compass needle is not pointing at something. It is responding to something. And that is a very different kind of knowing. The technical name for this planetary broadcast is the geomagnetic field. It extends from the molten core, travels upward through rock and soil and ocean, pierces the atmosphere, and reaches far into space, stretching outward in great invisible arcs called field lines, like the lines you would draw around a bar magnet with iron filings on a piece of paper. Scientists call it the magnetosphere. It is vast, it is ancient, and it is alive in the way that rivers are alive, not breathing, not conscious, but moving, shifting, responding to forces both internal and external. The magnetosphere reaches out about 65,000 kilometers on the side of the Earth, facing the Sun. On the opposite side, it stretches much, much farther, pulled into a long, flowing tail by the solar wind, that constant stream of charged particles the Sun throws outward in every direction. So the Earth's magnetic field does not sit still. It billows, it breathes, it responds. Every solar storm that the Sun produces, those massive eruptions of charged particles and radiation, physically pushes on the magnetosphere, compressing it, deforming it, causing it to ripple. And when you watch the aurora borealis, those pale green and violet curtains of light in the northern sky, you are watching charged particles from the sun collide with molecules in Earth's atmosphere, guided there by the very same magnetic field lines your compass is reading. The compass and the northern lights, the same force, the same invisible architecture. One fits in your hand, the other fills the sky. Now zoom in very close. Inside your compass needle, inside the thin sliver of magnetized metal, something extraordinary is happening at the level you cannot see. The needle is made of a ferromagnetic material, iron, typically, or an alloy of iron. And inside that metal, at the level of individual atoms, the electrons, those tiny particles that orbit atomic nuclei, are spinning. Not spinning metaphorically, literally spinning. Every electron has a quantum property called spin, and this spin creates a tiny magnetic field of its own. In most materials, adjacent electrons spin in opposite directions, and their fields cancel each other out. The material has no overall magnetism. But in iron and a handful of other materials, something different happens. The electrons align. Groups of them, sometimes millions or billions of atoms, all spin in the same direction, forming tiny regions called magnetic domains. In an ordinary piece of iron, these domains point in random directions, and again they cancel out. The iron has no overall magnetism, but when you magnetize iron, by exposing it to a strong magnetic field, the domains align. They all point the same way, and suddenly, the tiny spins of billions and billions of electrons add together into something you can feel, something that pushes and pulls. The compass needle is billions of electrons, all spinning in agreement, all pointing the same way. There is something deeply moving about that, if you let yourself feel it. The needle finds north because the electrons inside it are organized. They have been taught to agree, and when they agree, they hear the Earth's field. They feel its pull, and they respond. Agreement, at the atomic scale, creates the ability to listen. Before there were compasses, there were birds, and before the birds, there were fish, and before the fish, there were bacteria. Because the ability to sense the Earth's magnetic field, to feel which way is north, the way you might feel warmth from a fire, is not something humans invented. It is something life discovered. Long before the first human hand shaped the first tool. Long before the first civilization rose along the first great river. There were living things that had already been reading the Earth's magnetic field for hundreds of millions of years. There is a bacterium, a tiny, single-celled organism called Magnetococcus marinus. It lives in ocean sediment, in the dark, silty layers at the bottom of shallow coastal waters, where light barely reaches, and the world is made of mud and microscopic motion. And inside this bacterium, there are crystals, not large crystals, invisible crystals. Crystals made of magnetite, the same iron oxide mineral that gave rise to the first recorded observations of natural magnetism in human history. The mineral the ancient Greeks called lithos magnus, the stone from magnesia. Inside this single-celled creature, too small to see without powerful magnification, these crystals line up in a tiny chain. And that chain turns the whole organism into a living compass needle. When Magnetococcus marinus is trying to find the oxygen-poor sediment where it prefers to live, it does not use eyes, it does not reason, it does not navigate. It simply feels the angle of the Earth's magnetic field and swims along it, down toward the sediment, down toward the dark. One cell, no brain, no intention, just magnetite crystals and the Earth's ancient pull. The discovery of magnetotactic bacteria, that is the formal name for bacteria that navigate by magnetism, was one of those scientific moments that quietly reorders everything. Because once you know that a single cell can build its own compass from iron crystals, you start looking for magnetism everywhere in biology, and you find it. You find it in the beaks of migratory birds, where magnetite crystals may contribute to their extraordinary navigational ability, a subject that has consumed scientists for decades and is still not fully resolved. Still being argued over in academic papers and research stations from Finland to New Zealand. You find it in the cells of rainbow trout, in the tissue of sea turtles, in the bodies of honeybees. You find it, possibly, in the human body. There have been studies suggesting magnetite crystals may exist in the human brain, though what role they play, if any, remains deeply uncertain and quietly controversial. But the principle has been established. Life does not merely exist in the Earth's magnetic field the way a stone exists in a field. Passively, unresponsively. Life listens to it. Life has been listening to it since before the Cambrian explosion, since before complex multicellular creatures existed, since the very early chapters of biology on this planet. The compass, in other words, was invented long before the compass was invented. Biology got there first. Zoom out now, very far out. Not just to the surface of the Earth, not just to the magnetosphere, out to the cosmic scale. The Earth has a magnetic field because it has a liquid, conducting outer core that convects, that moves in currents driven by the temperature difference between the scalding inner core and the slightly less scalding mantle above. But not all planets do. Mars, our neighbor, our rust-colored cousin in the night sky, once had a magnetic field. Billions of years ago, Mars had a liquid, active core, and from that core, a magnetic field extended into space. And that field protected Mars the same way Earth's field protects us. Because here is one of the most astonishing facts about the geomagnetic field that most people never quite register. It is a shield. Not a metaphorical shield. A real, functional, life-enabling shield. The solar wind, that constant stream of charged particles the sun breathes outward at up to 800 kilometers per second, is not gentle. It is energetic and, in large doses, destructive to living tissue. It is also capable of stripping away a planet's atmosphere. And that is exactly what happened to Mars. When Mars's core cooled, when its magnetic field weakened and died, the solar wind began to slowly, patiently erode Mars's atmosphere. Over billions of years, it stripped away most of what Mars had. The planet dried. The oceans evaporated. The air thinned to nearly nothing. Mars became the red desert we see today because it lost its magnetic field. Earth still has one. Earth is still, in the most literal possible sense, alive because the iron in its core is still moving. And every time you hold a compass and watch the needle point north, you are holding a small piece of evidence that the shield is still up, that the core is still churning, that the planet is still protecting you. The compass is not just a navigation tool. It is proof of life. Imagine you are in a field in ancient Anatolia. The landscape is dry and golden. The air smells of dust and dry grass, and something mineral that rises from the earth when the heat is high enough. The sky is impossibly blue in that ancient pre-industrial way. A blue with no pollution in it, no particulate haze. Just pure atmosphere between you and space. You reach down and pick up a rock. It is ordinary looking, dark gray, almost black, dense, a little heavier than you might expect. But as you turn it in your hand, you notice something strange. There are iron fragments in the rock, small pins, old nails, flecks of iron ore that others have dropped, and they cling to your stone without being touched. Without any visible force, they just lean toward it. The way flowers lean toward light. You have just picked up a piece of lodestone. You have just picked up the world's first compass. Magnetite, the mineral contained within lodestone, is iron oxide. Specifically, it is Fe(O). 3 iron atoms bonded with 4 oxygen atoms. It forms deep in the earth, crystallizing from magma as it cools. In certain geological conditions, these magnetite crystals form in alignment with the prevailing magnetic field at the time of their formation, and they stay that way. frozen in magnetic time, preserving a record of the field direction that existed when the rock solidified. Lodestone is magnetite that has been magnetized naturally, usually by the intense, localized magnetic fields produced by lightning strikes. A bolt of lightning strikes the ground and passes through magnetite-rich rock. For a fraction of a second, an enormous current flows. The magnetic field produced by that current is powerful enough to align the magnetic domains in the magnetite. And when the moment passes, when the thunder rolls away and the storm moves on, the rock is changed. It is now a lodestone, a natural magnet, a stone that knows. And here is the haunting beauty of that transformation. The lightning does not intend to create a compass. The lightning is just energy, moving the way energy moves, finding the path of least resistance, expending itself. But in doing so, in that mindless, electric moment, it accidentally organizes something. It accidentally gives a rock the ability to respond to the planet's invisible music, creation through violence, order through chaos, a theme that will follow the compass for its entire existence. The ancient Greeks wrote about lodestone with a mixture of scientific curiosity and genuine awe. Thales of Miletus, one of the earliest pre-Socratic philosophers, a man who lived in the 6th century BC, and who we credit with some of the first attempts to explain the natural world without resorting to mythology, wrote about lodestone. He observed its ability to attract iron, and he concluded, in a move that was not unreasonable for his time and context, that lodestone must have a soul. He was not being metaphorical. Thales genuinely believed that the ability to cause motion, to attract, to pull, to reach out and move something without touching it, was evidence of an animating force, of life, of psyche. In his framework, things that could move other things were, in some sense, alive. And looking at a lodestone, watching iron pins creep toward it across a wooden surface, it is not hard to see why he thought so. The movement looks intentional. It looks like desire. The iron does not tumble toward the lodestone in a random, chaotic way. It moves smoothly, evenly, drawn by something that seems almost tender in its insistence, a gentle, unyielding pull, like the pull of memory, like the way the mind returns, unbidden, to a certain afternoon in childhood, a certain quality of light, a certain face, something invisible, reaching, something real. The ancient Chinese philosophers and scholars had their own encounter with lodestone, and their relationship with it was different, more practical, more directional. And here we must dwell for a moment, because what the Chinese discovered about lodestone was the first time in recorded human history that anyone noticed something remarkable. The stone did not merely attract iron. When floated on water or balanced on a smooth surface, the stone, or a needle touched by the stone, pointed south, not randomly, not vaguely, consistently, reliably, always the same direction, always south. Or, in the northern hemisphere, one end of the magnetized needle would point south and the other would point north. This was recorded during the Han Dynasty, sometime around the 2nd century CE, in a text called the Lunheng, written by the philosopher Wang Chong. He described the sinan, an ancient Chinese instrument consisting of a spoon carved from lodestone, balanced on a smooth bronze plate. When the spoon was set spinning, it always came to rest with its handle pointing south, not north, south. The Chinese called this direction south, the primary direction, the direction of warmth, of the sun's highest position, of summer and growth. North, in Chinese cosmology, was the direction of cold and darkness, of winter and stillness. So to them, the stone pointed toward warmth. It pointed toward life. And they called this device, this spoon of lodestone, a south pointer. Not a north pointer, a south pointer. The same instrument, the same magnetic force, the same invisible planetary signal, but pointed, in their understanding, in the opposite direction. Which raises a question that seems simple but cuts surprisingly deep. Which direction is the compass actually pointing? Is it pointing north, or is it pointing south? The answer is both, and neither. The compass is pointing along a line that has two ends, and we have arbitrarily decided to call attention to one of them. We named north, and called that the default. We built our maps and legends and cardinal systems around that choice. But the Earth itself has no preference. The field lines don't know they're going north. They're just going. And in that realization, in the understanding that the compass's direction is a human interpretation layered over a physical reality, something important shifts. We were not reading the Earth's mind. We were reading our own. There is a specific kind of courage that history has nearly forgotten how to name. It is not the courage of battle, which is visible, witnessed, surrounded by the noise and presence of other human beings. It is the courage of open water. The courage of climbing into a wooden vessel with swollen planks and stretched canvas sails and pushing away from land, from the last rock, the last tree, the last visible thing, and floating out into nothing, into gray-green water that extends in every direction with no edge, no landmark, no reference point, no way of knowing how far you have come or how far you have yet to go. For most of human history, ocean navigation was an art that lived entirely in the body and the mind of the navigator. The Polynesian wayfinders, those extraordinary sailors who colonized the vast Pacific Ocean centuries before European ships had any idea it existed, navigated by the position of the stars. The temperature of the water felt with a hand dragged over the side of the canoe, the height and period of ocean swells, the behavior of birds, the color of the clouds above distant land. They memorized star paths. They felt the way the ocean moved. They built stick charts, maps made of bent wooden sticks and shells that represented the pattern of ocean swells between islands, information that could only be read by lying in the bottom of a canoe and feeling the water move through the hull. They navigated with their entire bodies, and they were extraordinarily, almost incomprehensibly, accurate. But even they, those extraordinary wayfinders, could not navigate in the same way beneath a thick, overcast sky, or in seasons when the stars were wrong. Could not navigate in a storm-churned sea where the swells were chaos and the birds had fled and the stars were buried. The compass could. The first use of a magnetic compass for navigation at sea appears in Chinese records around the 11th century CE, during the Song dynasty. A document from 1088, written by the polymathic scientist and official Shen Kuo in his remarkable work Mongxi Bitan, a title often translated as Dream Pool Essays, describes magnetized needles and their navigational use. But the most vivid early account comes from another text of the same era, which describes Chinese navigators using magnetized needles that they floated in bowls of water or balanced on thin threads, watching them turn and settle to give direction when the stars were hidden. Not celebrating the tool, not marveling at it, just using it, in the matter-of-fact way that you use what you have always had. Which suggests that by the time it was being written down, the compass had already been in use for long enough that it had become ordinary, that the wonder had worn off, that the extraordinary had been domesticated. This is what humans do with magic. We turn it into procedure. The compass came to Europe through the Islamic world, carried along the same trade routes that carried silk and spice and mathematical notation, those invisible highways of knowledge that connected the medieval world from China to Andalusia. By the 12th century, European sailors were using magnetized needles. By the 13th century, the dry compass, a needle mounted on a pin inside a box, with a windrose diagram beneath, had appeared in the Mediterranean. And then, something extraordinary happened. Not slowly, with a kind of sudden, cascading force. The compass made long-distance ocean navigation possible in a way it had never been before. Not because the compass gave perfect accuracy, it did not. The magnetic North Pole is not the geographic North Pole. The difference between them, an angle called magnetic declination, varies from place to place across the Earth's surface, and ignoring that variation can take a navigator significantly off course. Early European navigators had to learn, through hard and sometimes fatal experience, that the compass needed to be corrected depending on where in the world they were sailing. But even with its imperfections, even with the complications of declination and variation, even with the crudeness of early instrument design, the compass gave navigators something that nothing else could, a reference point that did not require seeing. You could navigate in fog, in storm, at night, under cloud cover, in the deep winter darkness of northern latitudes where the sun barely clears the horizon. The compass didn't care about the weather. It didn't care about the time of day, or the season, or the thickness of the clouds. The Earth was always there. The field was always present, and the needle always felt it. Picture a ship at night, not a modern ship with its electric lights and GPS systems and radar displays. A medieval ship, a carrack or a caravel, 70 feet of oak planking and hemp rope and sailcloth, crewed by men who smell of salt and tar and fear. The ocean is black. The sky is black. The stars are hidden behind cloud. Every horizon looks exactly the same. Every direction is the same grey-dark nothing. And yet, the ship is moving. The sails are full of a wind the sailors can feel but not see. And at the stern, or in the waist of the ship, there is a man standing over a wooden box. Inside the box, in a small pool of light from a lantern, a needle trembles on its pin. The man watches it. He makes an adjustment, calls a word to the helmsman. The ship moves slightly, and the needle settles back to center. He is not using his eyes to navigate. He is not using the stars. He is communicating with the planet, through a box, through a needle, through the accumulated knowledge of what happens when certain minerals are exposed to certain fields. And the planet is answering. Go this way. Keep this bearing. Hold this course. Not in words, never in words. Just in the steady, quiet insistence of a needle that refuses to be wrong. The ocean crossing that the compass made possible, the European voyages of exploration from the 15th century onward, reshaped the world. That is not a comfortable sentence to sit with, and we should not rush past it. The compass was not a neutral tool that was used for neutral purposes. It was a tool that enabled an expansion of European power and reach that had consequences, cultural, demographic, ecological, political consequences that are still reverberating today, still shaping the world we live in, still causing conversations that need to be had. But the compass itself, the needle, the magnetized sliver of metal responding to the planet's field, the compass was neither good nor evil. It was simply sensitive. It was simply listening. And it showed the way to whoever was willing to use it. This is another of those truths about tools that is easy to miss, easy to skim past. A tool is not its use. A compass can guide a naturalist to the heart of a wilderness. It can guide a destroyer to a city that did not ask to be found. The needle does not choose. The earth does not choose. Only the hand that holds the compass chooses. And with that thought held gently, let's move on. Here is something that almost no one stops to consider. The North Pole is not where the compass points. Not exactly. Not even close. In some cases, the geographic North Pole, the axis around which the Earth spins, the point that all lines of longitude converge upon, the place you would find at the top of any conventional world map, is not the same as the magnetic North Pole. The magnetic North Pole is where the Earth's magnetic field lines converge vertically. It is the point where, if you held a dip needle, a compass needle balanced to rotate vertically rather than horizontally, it would point straight down into the Earth. And the magnetic North Pole moves. Not slowly, not imperceptibly. It moves. Over the course of the 20th century, The magnetic North Pole traveled from roughly northern Canada to the Arctic Ocean, migrating northward and then westward at rates that have varied considerably. In recent decades, it has been moving unusually fast, accelerating, in fact, from speeds of around 15 kilometers per year earlier in the 20th century to speeds of 55 to 60 kilometers per year by the early 21st century. Why is it moving? Because the fluid motions in Earth's outer core, those vast, slow currents of liquid iron and nickel, are changing. The churning is not constant. It is not uniform. Deep inside the planet, there are things happening that we cannot directly observe. Pressure changes, temperature fluctuations, variations in the way the liquid metal flows around the solid inner core. And as the currents in the outer core shift, the pattern of the magnetic field they produce shifts with them. The magnetic poles are not fixed. They are symptoms of a deeper, hidden process. And we are following them across the Arctic with GPS trackers, updating our magnetic charts every 5 years, recalculating the declination corrections that pilots and navigators and smartphone apps all rely on. We are chasing the planet's pulse, like a doctor pressing a stethoscope to a chest, trying to understand the rhythm underneath. Now here is the part that truly bends the mind. The magnetic poles have not merely moved. They have reversed, not once, not twice, but hundreds of times over Earth's history. A magnetic reversal, also called a geomagnetic reversal or a polarity reversal, is an event in which the north and south magnetic poles completely swap positions. Magnetic north becomes magnetic south, and vice versa. Your compass needle, in the middle of a reversal, would point south. The poles have reversed at irregular intervals, sometimes every few tens of thousands of years, sometimes remaining stable for millions of years, throughout Earth's 4.5 billion year history. We know this because rock preserves the memory of the magnetic field that existed at the time it formed. As magma cools and solidifies into rock, the magnetite crystals within it align with the prevailing magnetic field. They freeze in place, locked into the rock, recording which way north was at the moment of their formation. And when geologists examine ancient rocks from around the world, they find layers in which the magnetic orientation is exactly reversed from modern north. The geological record is a magnetic diary, a long, patient chronicle of a field that has changed its mind hundreds of times. The last full reversal occurred about 780,000 years ago, the Brunès-Matuyama reversal, as geologists call it. Before that, magnetic north was where we now call south, and a compass would have told every animal on Earth the exact opposite of what our compasses tell us today. And yet, during those reversed epochs, life went on. Birds still migrated, fish still navigated, bacteria still followed their magnetite crystals. Because north and south are not moral categories. They are not good and bad. They are just two ends of a line, and the line can point any direction at all. Life does not need north to be north. Life just needs the field to be there. Life just needs something to listen to. Between reversals, there are episodes called excursions, shorter-lived events in which the poles wander significantly, perhaps approaching a reversal and then pulling back. And there is a more troubling possibility that geophysicists have been studying with increasing intensity. The magnetic field is weakening. Over the past 2,000 years, a blink in geological time, but a very long time in human history, the overall strength of Earth's magnetic field has decreased by about 10 to 15%. That is not a reason for immediate alarm. Reversals take thousands of years to complete, and the field weakens significantly before reversing. But we do not know with certainty whether the current weakening is the beginning of a reversal or merely a fluctuation. There is an anomaly in the South Atlantic, a region called the South Atlantic Anomaly, where the field is measurably weaker than elsewhere, and where satellites passing through it experience increased radiation and sometimes computer glitches. Spacecraft operators are aware of it. They account for it. They worry about, quietly. The field that protects us, the field that the compass listens to. It is not permanent. It has never been permanent. It is dynamic, alive in its geological way, subject to forces we do not fully understand, expressing itself through processes we can only partially model. The compass is not pointing at something fixed and eternal. It is pointing at something that is still becoming, still changing, still deciding what it is. And in that, perhaps, the compass has more in common with us than we imagined. In the beginning, the needle was a splinter of lodestone, a fragment of the naturally magnetized rock, carved or shaped into a slender form and balanced on a pivot, or floated on a piece of straw in a bowl of water. Later, it was an iron needle, a sewing needle, the most slender and consistent piece of iron available, drawn across a piece of lodestone to induce magnetism, rubbed, carefully and repeatedly, in one direction only, along the grain of the lodestone's field. The rubbing had to be methodical, careful, patient, because the magnetism of the needle was fragile. It could be disrupted by heat. Heat above a certain temperature, called the Curie point, scrambles the alignment of magnetic domains and erases the magnetism entirely. It could be disrupted by mechanical shock, dropping the needle, striking it, subjecting it to vibration. And so the early compass maker was also a guardian of invisible order, a keeper of alignment, someone who knew that what they were protecting could not be seen. The Curie point, named for Pierre Curie, who discovered it in 1895, is the temperature above which a ferromagnetic material loses its permanent magnetism. For iron, the Curie point is about 770 degrees Celsius. Above this temperature, the thermal energy, the random, chaotic, heat-driven motion of atoms, becomes strong enough to overcome the alignment of magnetic domains. The electrons stop agreeing. The domains dissolve into randomness. The iron forgets which way is north. And here is the thing about this physical fact that should not be allowed to remain merely physical. There is a temperature at which everything falls apart, at which order becomes chaos, at which the patient, accumulated structure of a thing, the alignment, the agreement, the listening, dissolves back into noise. For iron, that temperature is 770 degrees. For other things, for institutions, for relationships, for beliefs, the temperatures vary, but the principle holds. Everything has a Curie point. Everything has a threshold beyond which the structure cannot maintain itself. The art of living, perhaps, is learning what that threshold is for the things you care about, and making sure they never quite reach it. The modern compass needle is not iron. It is a carefully engineered alloy, typically a combination of iron, nickel, aluminum, cobalt, and copper, selected for its magnetic properties, its resistance to demagnetization, and its ability to maintain alignment over time. The most common material for modern compass needles is alnico, an acronym for aluminum, nickel, and cobalt, an alloy that retains magnetism extremely well and resists demagnetization from mechanical shock and temperature variation. For specialized applications, for the super-precise compasses used in scientific research, or for the magnetometers aboard spacecraft, different materials are used. Rare earth magnets, containing elements like neodymium or samarium, produce fields many times stronger than iron magnets and maintain their magnetism with extraordinary stability. But the principle remains the same. Aligned domains, agreed electrons, a material that listens. And at the other end of the chain, at the receiving end, in a sense, is the Earth's field. Broad, diffuse, planet scale. The two fields, the tiny field of the needle and the vast field of the planet, interact. The needle's field is like a small voice trying to align itself with a vast chorus, and the chorus is patient. The chorus is always singing the same note, and eventually, after the needle settles, after the oscillations dampen, after the trembling stills, the needle adds its voice to the song and points. There is a form of compass that does not use a needle at all. The fluxgate compass uses coils of wire wound around a core of highly permeable magnetic material. An alternating current is passed through the coils, and the way the Earth's magnetic field distorts the current in the coils reveals both the direction and the intensity of the field. Fluxgate compasses are used in aircraft, in ships, in scientific instruments. They have no moving parts. They cannot be disrupted by vibration. They work upside down, sideways, at any orientation, and they are extraordinarily sensitive. A good fluxgate magnetometer can detect changes in the magnetic field on the order of a nanotesla, a billionth of a Tesla, the unit of magnetic flux density. To put that in perspective, the Earth's magnetic field at the surface is typically between 25 and 65 microtesla, million dots of a Tesla, far larger than nanotesla. So a nanotesla is a tiny, tiny fraction of the field these instruments are measuring. And yet, at that sensitivity, the instrument can detect not just the gross direction of north, but the subtle variations that occur hour to hour, day to day, as the solar wind pushes and pulls at the magnetosphere, as geomagnetic storms ripple through the field, as the slow, deep currents in the outer core produce their small but detectable fluctuations. At that sensitivity, the compass is not just listening to the Earth, it is eavesdropping on the sun. We have arrived at an interesting moment in the history of navigation. For almost all of human history, from the first hunter who looked up at the stars to the last generation before GPS became universal, finding your way required skill. It required knowledge. It required practice. It required, at some level, attention. You had to look at the sky. You had to read the landscape. You had to understand the relationship between the sun's position and the time of day. You had to know which stars were circumpolar, which rose and set, which could be trusted. You had to carry a map in your mind, or in your hands, or at the very least in your pocket. And if you got lost, truly lost, in the way that people used to get truly lost, you had to find yourself. Not metaphorically, literally. You had to look around, look up, look at the shape of the land and the direction of the light, and reason your way back to orientation. The compass was part of that process. It was a tool, but it was a tool that demanded engagement. You had to know how to use it. You had to know about declination. You had to take a bearing and maintain it, which required periodic attention, looking up from the compass, picking a landmark on the horizon, walking to it, taking a new bearing. Navigation, with a compass, was a conversation between you and the landscape. The compass started the sentence. You had to finish it. GPS has changed all of this in ways that we are only beginning to understand. The technology is astonishing. It is, without question, one of the most remarkable achievements of 20th century engineering. A constellation of satellites orbiting the Earth at an altitude of roughly 20,200 kilometers, each carrying an atomic clock of extraordinary precision, each broadcasting a continuous radio signal. Your device receives signals from at least 4 of these satellites simultaneously, calculates the tiny differences in the time it takes each signal to arrive, and from those differences determines your position on the Earth's surface to an accuracy of a few meters, or, for military-grade receivers and surveying equipment, to within a centimeter, in any weather, at any time of day, anywhere on the surface of the planet. The technology is, by any measure, a miracle. And yet there is something that has quietly gone missing. A study conducted by researchers at University College London found that people who used GPS navigation showed less activation in the hippocampus, the brain region responsible for spatial memory and navigation, than people who navigated using their own judgment. The GPS users were not engaging their spatial reasoning the way that unaided navigation requires. Another body of research has looked at London taxi drivers, a profession famously associated with extraordinary spatial memory. Since, until recently, candidates for a taxi license had to memorize the layout of the entire city, and found that the extensive hippocampal engagement required by that memorization was associated with measurable structural changes in the brain. Navigation, real navigation, the kind that requires paying attention, reasoning, remembering, building a mental model of where you are relative to where you've been and where you want to go. Navigation builds the brain. The compass, held in the hand, asked something of you. It asked you to look, to think, to engage with where you were. GPS says, don't think, just follow. And we follow. We follow a blue dot down streets we will not remember, toward places we will not quite be able to explain how to find again. This is not a polemic against technology. GPS saves lives. It prevents accidents. It allows emergency services to reach people who could not otherwise be found. These are not small things, but there is a loss too. A quiet, slow erosion of something that was built over tens of thousands of years of human movement across landscapes. The ability to know, in your body and in your mind, where you are. The ability to not be lost, not because a device tells you you're not lost, but because you genuinely, truly, deeply know. The Inuit peoples of the Arctic, one of the most remarkable navigational cultures in human history, developed a way of knowing the landscape that went far beyond what any instrument could provide. In a landscape with almost no features, flat, white, without trees or hills or rivers for much of the year, they navigated by the wind. The prevailing winds in the Arctic blow from consistent directions, and they sculpt the snow. They create long, parallel ridges in the snowpack called sastrugi, rippled, wave-like patterns in the snow that persist through the winter and point in consistent directions. An experienced Inuit navigator could read the sastrugi the way you read a compass, could feel, under the runners of a sled, the angle at which the sastrugi were being crossed, and know without looking up, without a compass, without GPS, which direction they were traveling. They navigated by texture. They navigated by touch. They carried the map inside the soles of their feet. We have largely lost this, not just Arctic peoples, but most of humanity. The intimate embodied knowledge of the land, the way your body learns to know a landscape through repeated passage over it, is something that GPS navigation actively discourages. Why memorize the route when the phone already knows it? But the phone doesn't know the landscape. The phone knows coordinates, and coordinates are not the same as here. The compass, for all its precision, for all its science, for all its role in the history of navigation, always required something from you that GPS does not. It required that you bring yourself to it, that you stand in a place and engage with it, that you turn your body until the needle lined up, that you look up from the compass and choose a bearing, that you walk toward something on the horizon and correct your course as the terrain shifted beneath you. The compass made you the navigator. The compass said, I will tell you which way is north. The rest is up to you. And that's worth something. That's worth a great deal, actually. The act of finding your own way, of genuinely not knowing where you are and then, through attention and reasoning, and the use of tools that still require judgment, arriving at an answer. That act is one of the deepest satisfactions available to a human body and mind. The relief of being lost and then found is not small, it is profound. The compass was the tool that mediated that relief for centuries, that trembling needle, that settling point. There, north is there. Now you know where you are. Every map that has ever been drawn began with a question. Not a technical question, not a mathematical one, a human one. Where am I? And every map that has ever been drawn, from the earliest scratches on clay tablets to the satellite composite digital maps we carry in our pockets today, is an attempt to answer that question in a way that other people can use. A map is a shared hallucination, a collective agreement that this symbol represents a mountain, that line represents a river, that color represents shallow water, and this other color represents depth. None of those things are the mountain, the river, the water. They are translations, approximations, conversations between the physical world and the human desire to understand it. And the compass is what made those translations meaningful. Because before the compass, maps were oriented by the things navigators could see, by landmarks, by coastlines, by the position of the sun at noon, which always fell in the south in the northern hemisphere, which is why early European maps were often drawn with east at the top, because east is where the sun rises, where the light begins, where things start. The word orientation comes from the Latin oriens, the east, the place of rising, the direction toward which early European maps were turned, tilted, held. To be oriented, in the original sense, was not to know where north was. It was to know where the dawn was. And then the compass came, and north became the reference point. Because the compass pointed north with unwavering consistency, regardless of the time of day, regardless of whether the sun was visible, regardless of season. And gradually, over centuries, maps rotated. North climbed to the top, and has stayed there ever since. But this choice, north at the top, is not a law of nature. It is a cultural habit, a convention that hardened into assumption, and then into something that feels as natural as the sky being above and the ground being below. Maps from medieval Europe sometimes had east at the top. Maps from early Islamic cartographers often had south at the top. The great 12th century Arab geographer Muhammad al-Idrisi, working in the court of the Norman King Roger II of Sicily, drew one of the most sophisticated maps of the medieval world and drew it with south at the top. If you flip an al-Idrisi map upside down, it suddenly looks very familiar, recognizable, almost modern. Nothing was wrong with his map, only his orientation was different. And yet we call maps like his upside down, as if up were a property of the earth and not of the mind. The compass gave us north, and north gave us power. Not in a conspiratorial sense, in a more subtle, more pervasive way. When north is up, the northern hemisphere is elevated. Literally, visually, on every map, it occupies the upper portion of the image, which the human visual system associates with dominance, with primacy, with importance. In the mental hierarchy we absorb from maps without realizing we are absorbing it, north is somehow above south, higher, more central. This is not cartographic truth. It is cartographic politics. The Mercator projection, the map most of us grew up with, the rectangular world map with its familiar distortions, dramatically inflates the apparent size of countries at high latitudes. Greenland appears roughly the same size as Africa on a Mercator map. In reality, Africa is about 14 times larger. This is not a conspiracy. It is a mathematical artifact of projecting a sphere onto a flat surface. But its effect is to make the northern regions of the world, Europe, North America, Russia, appear larger, more significant, more present than they actually are. And every child who has grown up with that map has absorbed a subtle, almost invisible message about the relative importance of different parts of the world. The compass pointed north. The maps put north on top. The projections made north look big. And we have been living inside those choices for 500 years. The compass did not intend this. The needle has no politics. But the world that the compass helped create, the world of ocean navigation, of colonial mapping, of territorial charting, that world made choices that still shape how we see and think and imagine the planet we live on. Now let us zoom in, very close, to a single room, in a single building, on a single winter afternoon, somewhere in 13th century Europe, perhaps England, perhaps France. The exact location doesn't matter. A monk is sitting at a table. He is copying a manuscript. The monastery is cold. His breath mists faintly in the air. The only light comes from a tallow candle that flickers when the wind finds its way through the gaps in the old stone walls. And on the table in front of him, beside the manuscript he is copying, there is a needle in a bowl of water. He is not navigating. He is not at sea. He will never go to sea. But the needle is there. He placed it there himself, earlier in the afternoon. He rubbed it on a lodestone as he had been shown, and then floated it on a piece of straw in the water. And he has been watching it settle, from time to time, between passages of text. He is not sure what compels him to keep looking at it, but he looks. And every time he looks, the needle is in the same position, the same sliver of iron, trembling in the same direction. He doesn't know the words magnetic field. He doesn't know the words geomagnetic force or ferromagnetism or outer core, but he knows something that we sometimes forget to know. In our age of explanation, that a thing can be real without being understood, that a truth can operate without being named. The needle points. He does not know why, and it is enough. It has always been enough. In the autumn, something happens in the trees. You might have noticed it without knowing you noticed it. A restlessness in the branches, a flocking, a gathering, an urgency in the air that has nothing to do with temperature, or not only temperature, a quality of movement that suggests direction, intention, departure. The birds are leaving, not randomly, not wandering. They are leaving in specific directions, toward specific destinations, across thousands of kilometers of ocean and continent and desert, to places some of them have never been before. A first-year Arctic tern, hatched in a colony in the high Arctic, will make a journey to the Antarctic before its first year is complete. A round trip that can exceed 70,000 kilometers, the longest migration of any animal on Earth, and it will make this journey for the first time, without parents to guide it, without landmarks for much of the route, without GPS. How? The answer is extraordinary in its multiplicity. Birds navigate using the sun. They use the stars. They use the polarization patterns of skylight, which they can apparently detect even when the sky is overcast. They use infrasound, low-frequency sound waves that they can detect with their inner ears. They use smell in some cases. They use visual landmarks when near coastlines. And they use the Earth's magnetic field. The precisely how of this has been debated, studied, contested, and refined for decades. And the picture that has emerged is both more complex and more wonderful than anyone first imagined. There are, as best as current research can determine, at least two separate magnetic sensing systems in birds. The first involves magnetite crystals, those same tiny mineral structures found in magnetotactic bacteria, which have been identified in the beaks and inner ears of various bird species. These crystals may function like a kind of compass, detecting the direction of the magnetic field. The second system is stranger, more mysterious, more poetic. It involves the eyes. In the retinas of migratory birds, there are specialized photoreceptor cells containing a protein called cryptochrome. Cryptochrome, when activated by light, undergoes a chemical reaction that produces a pair of molecules in a particular quantum state called a radical pair. The two molecules are entangled, their electrons are linked in a way that can only be described using quantum mechanics, a realm where the normal rules of classical physics become strange and insufficient. And the state of this radical pair, the way the electrons are spinning relative to each other, is sensitive to the magnetic field. The Earth's magnetic field influences the chemistry happening in the bird's eye. The bird literally sees the magnetic field, not in the way we see color or shape. Researchers think it may appear as a kind of overlay, a brightening or darkening of the visual field that corresponds to the direction of the field lines, as if north had a glow to it, as if the compass were painted on the inside of the eye. The bird's compass is in its vision. It navigates by seeing something we cannot see, by detecting a field that we cannot feel, by carrying, inside the chemistry of its retina, the same sensitivity to the Earth's field that we can only approximate with ground lodestone and steel and careful magnetization. There is a word for what we are describing. even though scientists are careful about applying it too broadly. The word is magnetoreception, the ability to receive, to sense, to detect, to respond to the magnetic field. It exists in various forms in a staggering array of living things, in birds, as we have seen, in sea turtles, which use the magnetic field not just for direction, but for position. Different parts of the ocean have subtly different magnetic field intensities and inclinations, and a sea turtle can read these variations as a kind of magnetic map, locating itself within the Atlantic with an accuracy that approaches GPS. In salmon, which use magnetic sensing to navigate from the open ocean back to the precise stream in which they were born, a river, a tributary, a specific stretch of water that they have not visited in years, that they know by the magnetic signature of the water. In honeybees, which have magnetite crystals in their abdomens and appear to use the field for various aspects of hive orientation and communication. And, perhaps, in humans. The evidence for human magnetoreception is tantalizing and contested. There are magnetite crystals in the human brain, specifically in the meninges, the membranes that surround the brain. They are abundant and well organized. They were discovered in the 1990s by Joseph Kirschvink at Caltech, who also coined the term magnetotaxis for the bacterial navigation behavior. What role these crystals play in human perception, if any, is unknown. There have been studies, some careful, some less so, suggesting that humans can subconsciously detect changes in the magnetic field, that our brains respond measurably to field shifts even when we are not consciously aware of them. But whether this rises to the level of a navigational sense, whether there is something it is like to feel north the way a homing pigeon feels it, this remains genuinely unknown. What we can say is this: the biological history of magnetic sensing predates the invention of the compass by hundreds of millions of years. Life was reading the Earth's field long before anyone thought to pick up a lodestone. The compass was not the beginning of navigation by magnetism. It was the first human attempt to copy something that nature had already perfected. Now, zoom out, all the way out, to the scale of migration itself. Every year, on a planet-wide scale, something extraordinary happens. Billions of animals move, not randomly, not chaotically. In streams and rivers and vast invisible flows, they travel along routes that have been refined by evolution over millions of years. Routes that follow the contours of the landscape and the patterns of the magnetic field. Routes that carry animals from feeding grounds to breeding grounds and back again, with a regularity that, from space, would look like the breathing of the planet. The Arctic tern traces a figure of 8 around the Earth. The monarch butterfly migrates from Canada to a specific mountain range in Mexico, generation after generation, even though no individual butterfly lives long enough to make the journey twice. The wildebeest circles the Serengeti. The whale swims from tropical breeding waters to polar feeding grounds and back. All of these movements are oriented. All of them are, in some degree, guided by the same magnetic field that guides the compass needle. The Earth's field is not just a navigation aid. It is the organizing principle of an entire planetary system of movement. It is the invisible highway along which the living world commutes. And the compass needle, that small, trembling, carefully magnetized sliver of alloy, is tuned to the same frequency. It joins the migration. It joins the great, ancient, invisible river of magnetic orientation that runs through all of living history. A human artifact, a piece of engineered metal. And yet it listens to the same signal that the first magnetotactic bacteria listened to. 500 million years ago, the needle and the bacteria, the compass and the tern, all hearing the same note, all pointing the same way. There is a map in a museum in Florence. It is called the Carta Pisana. It is made of vellum, thinly scraped sheepskin, soft and pale, marked with thousands of careful pen strokes. It dates to approximately the late 13th century, making it the oldest surviving sea chart of the Mediterranean world. It is beautiful, and it is precise, unnervingly, astonishingly precise for an object made without modern instrumentation, without satellite data, without anything beyond direct observation, measurement, and mathematics. The coastlines of the Mediterranean are rendered with an accuracy that would not be significantly improved for another 2 centuries of cartography. This is the compass's doing. The Portolan charts, the navigational sea charts of the medieval Mediterranean, of which the Carta Pisana is the oldest survivor, were drawn using compass bearings. A navigator would observe the direction of one port from another, note the distance sailed, and plot the result on the chart. Over many voyages, over many observations, the charts accumulated data. And because the compass gave consistent, reliable direction, the accumulated data was consistent and reliable. The charts were not made by a single person. They were made by the sea, by thousands of voyages, by the patient accumulation of compass readings taken on thousands of mornings and evenings over generations of Mediterranean sailors. The compass drew the coastlines of the world, not the hand that held it, not the eye that read it, the needle. When Vasco da Gama rounded the Cape of Good Hope in 1497 and opened the sea route from Europe to India, he carried a compass. When Columbus made his first crossing of the Atlantic in 1492, he carried a compass. When Magellan's fleet began the first circumnavigation of the globe in 1519, compasses were among the most important instruments aboard. These voyages remade the world. They established trade routes that channeled immense wealth from east to west. They initiated the colonial period, that long, violent, complicated era of European expansion that determined the political geography of the planet we live on today. They brought diseases that decimated indigenous populations. They brought enslaved people across oceans in conditions of horrific suffering. They brought animals and plants to new continents, changing ecosystems permanently. The compass was in the hand that held the rudder. The compass was in the hand that drew the treaty lines on maps. The compass was in the hand that pointed at a coast and said, "This is ours now." And here is the philosophical weight of that. An instrument of extraordinary sensitivity. An instrument that listened to the planet's deepest, oldest, most fundamental signal. An instrument that, in its most essential nature, was about receiving, about being quiet enough, aligned enough, to feel what was already there, used in service of the loudest, most violent, most disruptive project in the history of human civilization. The compass navigated the ships of empire. The compass found the routes that changed the world, and the needle, through all of it, did nothing but point, did nothing but tremble, and still, did nothing but listen to a field that does not know about borders, does not know about ownership, does not know about the difference between one coast and another, one people and another, one civilization and another. The Earth's magnetic field does not observe the lines we draw on maps. It ignores them entirely. It just pulls the needle, and the needle points. There is a quieter story inside the story of empire and exploration. It is the story of the navigators themselves, not the admirals and captains whose names made it into history books, the ordinary sailors, the men who spent weeks, months, sometimes years at sea, who slept in hammocks strung in the dark damp below decks, who ate salt pork and hardtack and drank water that had been in barrels long enough to grow things, who suffered from scurvy, a disease of vitamin C deficiency that causes the gums to bleed, the teeth to loosen, old healed wounds to reopen, who lived with the constant quiet knowledge that if the ship foundered, if a storm caught them wrong, if the hull sprung a leak that outpaced the pumps, there would be no rescue. The ocean was too large, and the world too slow for rescue. These men trusted the compass, not in a sentimental way, in the most practical, most concrete, most necessary way imaginable. The compass was one of the very few certainties on an ocean full of uncertainty. They knew it could be trusted, because it had been trusted before. by others, and those others had arrived. When you are weeks from land, with no landmarks and a sky full of clouds, the sight of the compass needle pointing steadily in its familiar direction is not a small thing. It is not merely technical. It is, in the most fundamental sense, comfort. Something that knows where it is, something that does not waver, something you can check in the dark, on a rolling deck, in the middle of the night when the sea is grey and the horizon is invisible and every direction feels exactly the same. You can check it, and it will tell you, and you will know. Every compass has two poles. The north-seeking end, painted red in modern compasses, the color of urgency, of blood, of importance, and the south-seeking end, painted black, or white, or sometimes not marked at all, as though it were the lesser half, the shadow, the part that matters less. But the two ends are not unequal. They are bound. You cannot have a North Pole without a South Pole. You cannot separate them. This is one of the most fundamental rules of magnetism, a rule with no exceptions that have ever been observed. Magnetic monopolies do not exist in nature. Every magnet has two poles. Every field has two directions. Every needle has two ends. In electromagnetism, there is a concept called duality, the way in which certain seemingly opposite things are actually two aspects of the same thing. Electric fields and magnetic fields are related in this way. They transform into each other depending on the reference frame of the observer. North and south are not opposites. They are partners. They are what the field looks like from the two ends of the same line. And here, if you are willing to let a small idea expand into a larger one, there is something worth sitting with. We live in a culture that loves to separate opposites, good and evil, light and dark, past and future, beginning and end. We treat these as different things, as contradictions, as irreconcilables. But the compass suggests a different way of seeing. Perhaps some things that appear to be opposites are actually two poles of the same magnet, two ends of the same needle, inseparable, defined by each other, each one meaningless without the other. And now we arrive at the midpoint of our story, the place where, in every compass tale, something shifts. Because a compass is a navigator's tool, and navigation implies a journey, and every journey, eventually, ends. The ship arrives at port. The expedition returns from the wilderness. The traveler reaches home. And when the journey ends, what happens to the compass? For centuries, the answer was, it waits. It sits in a case or a drawer or a coat pocket, not currently in use, but available, ready, still aligned, still listening. But there are other endings that are more final. Compasses that are dropped in rivers, compasses that burn in fires, compasses aboard ships that sink, compasses left behind in abandoned places, in the pockets of coats left hanging, in the drawers of desks in houses that were demolished, in the kits of soldiers who did not come back. Compasses that are no longer needed, no longer maintained, no longer consulted. What happens to a compass when its navigating days are over? What happens to the needle when the hand that held it stills? There is a compass at the bottom of the ocean. Not one compass, many. Ships have been sinking since ships have been built. And for the last several centuries, those ships carried compasses. Some of those ships lie in shallow water, accessible to divers. Some lie in the crushing darkness of the deep ocean, 3 kilometers down or more, where no light has ever reached, where the pressure is enough to collapse a submarine like a paper cup. And in those ships, in their broken hulls, in their silt-covered remains, the compasses lie, still intact in many cases. The glass may be cracked, the brass may be corroded, turned green by long immersion in seawater. The card beneath the needle may have dissolved, or may have been preserved by conditions no one predicted. But the needle, in many cases, still points, not to a harbor that the ship was heading for centuries ago, not to a destination that was lost when the ship went down. It points north. The same north it always pointed. The same field it always heard. 3 kilometers below the surface of the Atlantic, in total darkness, in silence, on the tilted deck of a ship that has not moved in 300 years. The needle points north, because the Earth's field reaches down there, because the magnetosphere does not stop at the ocean surface, because the invisible force that organized the electrons in the needle all those centuries ago is still there, still present, still broadcasting. The compass at the bottom of the ocean is still navigating, still oriented, still doing the only thing it ever knew how to do, even though there is no one left to read it. This is the midpoint. This is where, in our story, the primary life of the compass comes to rest. Not with drama, not with ceremony, with quietness, with the image of a needle pointing north in the dark. Because that is what endings actually look like. Not explosions, not fanfare, just function. Continuing past the moment when anyone needs it to function. A habit of being that has outlasted its context. And now the real wonder begins. Because what happens next, in the second half of this story, is not the story of the compass as a tool. It is the story of what the compass becomes, what it teaches, what it dissolves into, what grows from the ground where it rests. It is the story of the afterlife of the needle, and it is more beautiful than the life that came before. When a compass is demagnetized, when its needle loses the alignment of its magnetic domains, when the electrons stop agreeing, when the subtle, carefully organized order within the metal dissolves back into randomness, something interesting happens. The needle does not die. It does not cease to exist. It is simply no longer organized in the way it was. The metal is still there. The iron, the nickel, the cobalt. The atoms are all present, still bound to each other in the same crystalline structure as before. But the domains have scattered. The electrons are spinning in random directions again. The agreement is gone. A demagnetized compass needle is, at the atomic level, a kind of democracy gone quiet. 1,000 voices that once sang in unison, now all singing different notes. But they are still singing. The potential for alignment is still there. Touch the needle to a strong magnet, and the domains will organize again. Apply a strong magnetic field, and the electrons will align. The needle will point north again. The compass can be resurrected. The order that was lost can be restored. Not the same order, not the same specific alignment of every domain exactly as it was, but an equivalent order, a new agreement, a new listening. What this means in the soft physics of metaphor is something worth pausing on. Nothing is permanently lost, not in matter, not in magnetism, not in the patient, particular world of physics. The potential is always there. The capacity to be organized, to be aligned, to listen. It doesn't go away when order breaks down. It waits. There is a geological phenomenon that serves as the most profound illustration of the compass's afterlife. It is called paleomagnetism, and it is, in its quiet way, one of the most beautiful things in all of science. When molten rock, magma, lava, cools and solidifies, the magnetite crystals within it align with the prevailing magnetic field at the moment of solidification. They freeze in place. They record, permanently, reliably, over millions and sometimes billions of years, exactly which direction magnetic north was pointing when that particular rock was born. The rock becomes a compass. Not a compass you can hold in your hand and read by looking at a needle. A compass you read with instruments, carefully extracting the magnetic signal from the rock, measuring the direction it points, calculating the intensity of the field it recorded. A compass of stone. A compass that does not move, that cannot be consulted in the middle of the ocean. But that tells a different kind of story, a much, much older story. Paleomagnetism was the key that unlocked plate tectonics. This is one of those moments in the history of science that deserves to be told slowly, because the implications are so enormous that they can easily slip past if you're not paying attention. In the 1950s and 1960s, Oceanographers were mapping the floor of the ocean. They had expected the ocean floor to be ancient, stable, uniform. A vast plain of old rock, relatively featureless. What they found instead was astonishing. The ocean floor is cut by great ridges, enormous underwater mountain ranges that run for thousands of kilometers. The most prominent, the Mid-Atlantic Ridge, runs almost the entire length of the Atlantic Ocean, from Iceland in the north to near the Antarctic in the south. And at these ridges, something extraordinary is happening. New ocean floor is being created. Magma wells up from deep within the earth, pushes out along the ridge, cools, and solidifies. The ocean floor is not old and static. It is young at the ridges and old at the edges of the ocean, where it dives back into the mantle in a process called subduction. The ocean floor is a conveyor belt, constantly created at the ridges, constantly destroyed at the margins. And as they mapped the magnetic properties of this new ocean floor, the oceanographers found something that should not have been possible if the old view of a static ocean were correct. The ocean floor was striped. In alternating bands, parallel to the mid-ocean ridges, the rock recorded alternately normal and reversed magnetic polarity. A stripe of rock pointing normal north, then a stripe pointing reversed north, then normal again, then reversed. Symmetrical on both sides of the ridge, like a mirror image, like a recording. This was the pattern of geomagnetic reversals, recorded in the ocean floor as it spread. As the planet's magnetic field reversed over geological time, sometimes pointing normal, sometimes reversed. The new ocean floor being created at the ridges recorded each reversal like a tape recorder. The ocean floor is a magnetic diary, a permanent, massive, planet-scale recording of every time the Earth changed its mind about which way was north. And this discovery, this reading of the compass in the rock, confirmed plate tectonics, confirmed that the continents move, that the ocean floor spreads, that the solid surface of the Earth is not solid in the sense we imagine when we stand on it and feel its unyielding hardness, but is in motion, is flowing in geological time, is reshaping the planet on timescales that dwarf everything in human experience. The compass in the rock told us that the world is alive, that the ground beneath our feet is moving, that the very planet we live on is a work in progress. And here is the zoom out that this deserves. The continents we live on, the land masses that define the borders of nations, that have been the stages for all of human history, that we name and claim and fight over and build on and call home, they are where they are because of plate tectonics. The Himalayas exist because the Indian plate collided with the Eurasian plate. The Alps exist because the African plate is pressing northward. The Andes exist because the Nazca plate is diving beneath South America. The Atlantic Ocean exists because a supercontinent called Pangaea began to break apart roughly 175 million years ago, and the pieces drifted apart, slowly, over geological time, carried on the slow conveyor of the ocean floor. All of this was confirmed, not suspected, not theorized, but scientifically confirmed, by reading the compass in the rock, by measuring the magnetic signal locked into the ocean floor, by listening to the Earth's own recording of its past. The compass did not just navigate ships. The compass, in its afterlife, in its existence as a frozen geological record, revealed the shape of the world, told us how the continents formed, told us how the mountains rose, told us where we came from, in the deepest, most literal, most geological sense. Underscore, there is a mineral called hematite. Its name comes from the Greek word for blood, haima, because when hematite is powdered and mixed with water, it runs red. Hematite is iron oxide, a cousin of magnetite, the mineral in lodestone. And like magnetite, it is present in ancient rocks throughout the geological record. But hematite does something that gives geologists an extraordinary window into the past. When hematite crystals form in sedimentary rock, when tiny particles of hematite settle through water and are buried and slowly compressed into stone. They align with the prevailing magnetic field of the moment. They remember it. They carry, inside themselves, the direction of north from the moment they settled. From the moment the water was still enough, the pressure was right. The conditions were perfect for the memory to be preserved. And some of those memories are very, very old. The Jack Hills of Western Australia contain zircon crystals, not magnetic, but useful for radiometric dating, that are 4.4 billion years old, the oldest known minerals on Earth, preserved from an era so early in Earth's history that no continents existed yet, no oceans as we know them, no life. And in other ancient rocks, geologists have found paleomagnetic signals that reach back nearly 3.5 billion years. The compass memory in rock goes back almost to the beginning, to an Earth that was barely recognizable, hot, bombarded by asteroids, covered in shallow seas and volcanic archipelagos, an atmosphere of nitrogen and carbon dioxide and hydrogen sulfide, with no free oxygen, an alien world. But already, even then, the magnetic field was there. Even then, the planet was already broadcasting, already organizing the electrons in the cooling rock, already writing its diary, and we can read it today. We can hold a piece of ancient Australian rock, a piece of Earth that was born when the solar system was young, when the sun had barely settled into its current form, before there were animals, before there were plants, before there was anything that could look up at the sky. And we can read which way was north. We can reconstruct the location of the magnetic pole in a world that no longer exists. We can follow the planet's memory, all the way back to the beginning. Zoom in now. Past the rock, past the mineral, past the crystal lattice of hematite or magnetite, down to the atom, the iron atom. Iron is the 26th element on the periodic table. Its atomic nucleus contains 26 protons, and in its most common form, 30 neutrons. Around that nucleus, 26 electrons occupy orbitals in the strange, probabilistic way that electrons inhabit space. It is the arrangement of those 26 electrons that makes iron special. Iron's electron configuration leaves 4 unpaired electrons in its outer shell. These 4 electrons have parallel spins. They spin the same way, rather than pairing up and cancelling each other out. And because of those 4 unpaired spins, each iron atom is a tiny magnet, a tiny, permanent, constantly active magnetic dipole. In most materials, neighboring atoms have their magnetic moments pointing in random directions, and everything cancels. But in iron, there is a quantum mechanical effect, something called exchange interaction, that causes neighboring iron atoms to prefer aligning their magnetic moments in the same direction. This is the origin of ferromagnetism. This is why iron is magnetic in a way that most materials are not. 4 unpaired electrons, spinning in parallel, causing their neighbors to follow suit, and the neighbors causing their neighbors, until vast domains of billions of atoms are all aligned, all pointing the same way, all listening to the feel. And here is the thought I want you to hold. That alignment, that agreement between neighboring atoms, that tendency for one iron atom to influence the next, to encourage it to spin the same way, is not imposed from outside. It is not the magnetic field that creates the alignment within the domain. The alignment within the domain comes from the atoms themselves, from the way iron atoms prefer to relate to their neighbors. The external field merely gives the domains a common direction, but the internal coherence, the agreement within the domain, that comes from the nature of iron itself, from the way iron is made. The compass is not just an object that responds to the world. It is an object whose internal nature makes it want to be organized, makes it want to agree. And that is a quality worth admiring in anything that has it. The magnetic field of the Earth does not merely record the history of the planet. It actively shapes the living world, not just in the ways we have discussed: the migration routes, the biological compasses, the navigational sense of birds and turtles and fish, but in ways that are quieter, more subtle, more surprising. Soil bacteria, the invisible ecosystem that lives in every handful of garden soil, are subject to the Earth's magnetic field in ways that affect their growth and behavior. Some species grow differently when the field is experimentally altered. Some move toward or away from field sources in ways that are not fully understood. Plant roots show a tendency to grow in alignment with the magnetic field, a phenomenon called magnetotropism, which may influence how root systems develop, how plants orient themselves underground where light is not a guiding force. There is evidence that some plants use the magnetic field as a reference for the direction of their growth, the same way they use light, not primarily, not instead of phototropism, but as a supplementary cue. Honeybees, as we mentioned, have magnetite crystals in their abdomens, but their use of the magnetic field goes beyond simple navigation. They appear to use it in the construction of their combs, orienting the comb structure in specific ways relative to the field. They have been observed changing their behavior in response to changes in the local magnetic field, becoming more agitated during geomagnetic storms, more quiescent in stable conditions. The hive has a relationship with the planet's field, a relationship that predates the hive, predates the bee, predates everything complex enough to have a relationship with anything. And now, one of the most extraordinary examples of the compass's influence on life: magnetite in the human heart. Not the metaphorical heart, the physical one, the fist-sized muscle that beats approximately 100,000 times each day, pumping 5 liters of blood per minute through the 100,000 kilometers of blood vessels in your body. The iron in your blood, hemoglobin, the protein in red blood cells that carries oxygen, contains iron. When hemoglobin is bound to oxygen, it is slightly diamagnetic. It is very weakly repelled by magnetic fields. When it releases oxygen and becomes deoxyhemoglobin, it becomes slightly paramagnetic, very weakly attracted by magnetic fields. This difference, tiny, barely measurable, is the basis of a technology called bold fMRI, which stands for blood oxygen level dependent functional magnetic resonance imaging. When a region of your brain becomes active, when you think a thought, feel an emotion, solve a problem, recall a memory, blood flow to that region increases. The ratio of oxygenated to deoxygenated hemoglobin changes. And because of the different magnetic properties of these two forms of hemoglobin, a magnetic field can detect that change. An MRI scanner applies a powerful magnetic field, typically 1.5 to 7 Tesla, compared to the Earth's field of about 0.00005 Tesla, roughly 30,000 to 140,000 times stronger, and detects the tiny differences in magnetic response from different regions of the brain. The result is a brain scan, a map of activity, a picture of the living mind at work. The compass, scaled up to industrial power, peering into the most complex object in the known universe, reading the brain the way the brain reads the world. The medical applications of magnetic sensing have quietly transformed medicine in ways that many people don't fully register as being related to the compass. Every MRI scan is based on the same fundamental principle as the compass. Every MEG scan, magnetoencephalography, which measures the tiny magnetic fields produced by the electrical activity of neurons, is listening to the brain the same way the compass listens to the Earth. Magnetometers are used to detect iron accumulation in the liver, a sign of hemochromatosis. They are used to measure the magnetic fields of the heart, magnetocardiography, detecting arrhythmias and other cardiac abnormalities with extraordinary sensitivity. The compass has become a medical instrument. The compass reads the body the same way it reads the planet, because the body, like the planet, has a magnetic field, not a large one. The magnetic field produced by the electrical activity of your brain is roughly 1 billion times weaker than the Earth's field. Measuring it requires instruments of extraordinary sensitivity, shielded from environmental interference, cooled to near absolute zero with liquid helium. But it is there. Your thoughts have a magnetic field. Your heartbeat has a magnetic field. You are broadcasting right now a magnetic signal, Tiny, incredibly tiny, but real. You are, in the most literal possible sense, magnetic. A compass needle retired from use, demagnetized, corroded, set aside, left in a drawer for years, then decades, then forgotten. Eventually it enters the earth. Perhaps it is thrown away and ends up in a landfill. Perhaps it is abandoned in a house that is eventually demolished. Perhaps it falls into a river or a stream and is carried downstream, tumbling with the current, becoming smaller as it is worn by the water and the sand. However it happens, the iron makes its journey back, because iron, on geological timescales, returns. It oxidizes, it rusts, it combines with oxygen in the air and water to form iron oxides, compounds like hematite and goethite and ferrihydrite, the same mineral families from which lodestone was born. The process takes years, decades, centuries, but it happens. The magnetized needle becomes, eventually, a kind of iron oxide dust, dispersed, returned to the soil. Entering the food chain, plants absorb iron from the soil, animals eat the plants, and the iron from the compass needle may, centuries after the compass ceased to exist as a compass, be circulating in the body of a living creature. The iron that was once organized into a magnetic domain, the iron that once pointed north, now dispersed, recycled, anonymous, but still iron, still carrying, at the atomic level, those 4 unpaired electrons, still potentially alignable, if the conditions were right, still, in its quiet, atomic way, capable of listening. The iron cycle. This is what biogeochemists call the pathway that iron takes through the living world. Iron is not a passive element. It is one of the most biologically active metals on the planet, and its availability, or lack of availability, constrains life in enormous parts of the ocean. In the open ocean, far from continents, far from the dust blown off deserts and the rivers that carry sediment to the sea, iron concentrations are extraordinarily low. Sometimes as low as 0.02 nanomolar. That is, roughly 200 million times lower than your blood's iron concentration. And yet, phytoplankton, the microscopic photosynthesizing organisms that produce roughly half of Earth's oxygen and form the base of the ocean food chain, require iron to function. They need it for the enzymes that fix carbon dioxide, for the proteins that carry electrons in photosynthesis. Without iron, phytoplankton cannot bloom, and without phytoplankton blooms, the ocean is relatively empty. Iron is the limiting factor for life across much of the world's ocean. And where does that ocean iron come from? Some of it falls from the sky, iron-bearing dust, blown from deserts like the Sahara, traveling thousands of kilometers across the Atlantic and Pacific, falling into the sea. Some of it wells up from the deep ocean, where iron-rich water rises from hydrothermal vents. Some of it comes from rivers, and some of it, some infinitesimally small fraction of it, may be the iron from instruments humans have made and lost and discarded. The compass joins the iron cycle. The needle joins the living ocean. The magnetized metal dissolves into the chemistry of life. And somewhere in the chain, in the bloom of phytoplankton, in the small fish that eats the phytoplankton, in the large fish that eats the small fish, in the whale that eats the large fish, in the cloud of whale breath misting above the ocean surface, somewhere in that long, complex, beautiful chain, the iron of the compass lives on, still active, still doing what iron does, still, in its way, pointing. A compass points. This is what it does. This is what it has always done. But what does it mean, really, deeply, philosophically, to point? A compass does not choose its direction. It does not deliberate. It does not consider options. It does not weigh the advantages of north against the advantages of south and make a reasoned decision. It points because the physics of its construction, in contact with the physics of the planet, produces pointing. It is not a decision, it is a consequence. And yet we trust it more than almost any other instrument. We trust the compass precisely because it doesn't choose. We trust it because it cannot lie. Because between the compass and north there is no human interpretation, no political agenda, no uncertainty of intention. The needle points because the earth pulls. That's all. That's everything. There is a teaching in Zen Buddhism, one of those brief koan-like observations that opens the more you look at it, that goes something like this. Before enlightenment, chop wood, carry water. After enlightenment, chop wood, carry water. The activities are the same, but the relationship to the activities is different. The chore is the same chore, but the one doing the chore is not the same. I think about this in relation to the compass. Before you understand the compass, the needle points north. After you understand the compass, after you know about the molten outer core, the magnetotactic bacteria, the reversals, the paleomagnetic record, the quantum chemistry in the bird's eye, the needle still points north. The fact is the same, but the fact is not the same, because now you know what is behind it. You know that the needle is connected by invisible threads of physics to the entire history of the planet, to the first bacteria that built their own compass from iron crystals, to the ocean floor stripes that confirmed continental drift, to the aurora borealis, to the migratory arc of the Arctic Tern, to the deepest, oldest, most fundamental force that the Earth exerts on the living and non-living world. The needle hasn't changed. Your relationship to the needle has. And that is what understanding does, when it is the right kind of understanding. It does not take away the wonder. It feeds it. It gives the wonder roots. Here is a question worth holding. If you were to design a navigation tool from scratch, if you were given the laws of physics as a starting point, and asked to create the simplest, most reliable direction-finding instrument possible, could you do better than the compass? It requires no power source. It requires no signal from satellites. It cannot be jammed or spoofed or interfered with by anything other than a very strong local magnetic field. It works underwater. It works underground. It works in the dark, in storms, in conditions where every other navigation technology fails. It requires no maintenance, beyond keeping the needle magnetized and the pivot clean and the housing intact. It will work for as long as the Earth's magnetic field exists, which means it will work for at least hundreds of millions of years into the future, assuming the field doesn't reverse, and even if it reverses, the compass will still work. It will just point in the opposite direction. No technology we have developed in 5,000 years of toolmaking has quite matched this combination of simplicity, reliability, and endurance. The compass was not superseded by GPS. It was supplemented by GPS. The difference matters. GPS is more precise. GPS is more informative. GPS tells you not just which direction you're going, but exactly where you are and how long it will take to get to where you're going. But GPS can fail. GPS can be spoofed. It can be jammed. It can be disrupted by solar storms that affect satellite signals. It can fail when the battery dies, when the satellite connection is lost, when the hardware breaks. Every naval vessel in the world still carries magnetic compasses. Every aircraft cockpit still has a magnetic compass. Every wilderness survival kit recommends carrying a magnetic compass, because there will be moments, there will always be moments, when everything else fails. And the needle, without batteries, without signals, without any technology more complex than a magnetized piece of alloy on a pivot, will still be doing the only thing it knows how to do: listening, pointing, being still in a direction that is never still. We have arrived at the frontier, not the frontier of geography, not the frontier of history, the frontier of understanding itself, the place where the known world ends and the genuinely, beautifully unknown begins. And at this frontier, the compass has arrived before us. Because the most extraordinary thing about the compass, the thing that researchers are still unwrapping, still arguing about, still staying up late to think about, is not what we have already described. It is what happens in the eye of a robin, the European robin, Erithacus rubecula, a small bird, 11 to 14 centimeters long, weighing between 16 and 22 grams, orange-red breast, brown back, dark eyes that seem, in certain lights, to hold a knowledge they should not have. This bird migrates from breeding grounds in northern Europe to wintering grounds in the south, and back again. A journey of hundreds, sometimes thousands of kilometers, and it navigates, in part, by seeing the Earth's magnetic field, not metaphorically, not approximately, literally. Inside the retina of the robin's eye, in specialized cells called double-cone cells, there is a protein called cryptochrome 4. When light, specifically blue light, strikes a cryptochrome molecule, it excites an electron, kicking it from one part of the molecule to another. This creates what physicists call a radical pair, two molecules, each with an unpaired electron. And these two electrons are in a quantum state called entanglement. Their fates are linked. What happens to one is not independent of what happens to the other. Even though they are spatially separated, they are connected by the most fundamental, most mysterious principle of quantum mechanics. And here is the astonishing part. The state of this entangled radical pair, whether the electrons are spinning parallel or anti-parallel to each other, is sensitive to the magnetic field, specifically to the inclination of the Earth's magnetic field, the angle at which the field lines dip relative to the horizontal. This angle changes with latitude. At the magnetic poles, the field lines are nearly vertical. At the equator, they are nearly horizontal. So as the robin moves north or south, the inclination of the field changes, and the cryptochrome in its retina detects this change. The chemistry in the eye shifts, and the bird sees something, some visual signal, some brightening or dimming or patterning in its visual field that tells it which way the field is inclining, which tells it, in a way no compass can precisely replicate, not just which direction is north, but where it is on the Earth. This is what north feels like at this latitude. This is home. This is where I turn. The radical pair mechanism is quantum biology. It is quantum physics operating in a warm, wet, biological system. And this should not work. Quantum coherence, the preservation of quantum states like entanglement, is extraordinarily fragile. It is typically destroyed almost instantly by thermal noise, by the random jostling of atoms in a warm environment. Quantum computers work only at temperatures near absolute zero, because the slightest warmth destroys the quantum states they depend on. And yet, in the eye of a robin, at body temperature, in a wet and metabolically active tissue, the radical pair appears to maintain quantum coherence for long enough to detect the magnetic field, tens of microseconds, maybe more. Long enough. Precisely long enough. How? This is one of the most actively debated questions in quantum biology. How does biology maintain quantum coherence in conditions where quantum mechanics says it should be impossible? Some researchers believe the protein structures surrounding the cryptochrome molecules are shaped in ways that protect the radical pair from thermal noise. That evolution has, over hundreds of millions of years, shaped a molecular architecture that buffers quantum states against the destructive warmth of biology. That life has learned to use quantum mechanics. Not by going cold, by going careful, by building, at the molecular scale, structures so precisely shaped that they hold the fragile quantum state together long enough to do its work. And if life can use quantum mechanics for navigation, if the robin's eye is a quantum compass, then what else might life be doing with quantum physics that we have not yet noticed? This question is the open door at the edge of our current understanding. Photosynthesis, some researchers believe, uses quantum coherence to transfer energy through the photosynthetic reaction center with near-perfect efficiency. Enzyme catalysis may use quantum tunneling. the ability of particles to pass through energy barriers that classical physics says they cannot cross, and consciousness itself, the most mysterious thing in the universe, the thing that allows you to be aware of these words as you hear them. Consciousness may have quantum mechanical underpinnings that we are only beginning to theorize about. The compass, in its quantum biological form, is a window into a possibility that reorganizes everything. The possibility that life is not merely classical, that biology is not just chemistry running on Newtonian physics, that living things are, at their most fundamental level, quantum systems. Systems that use entanglement, that use superposition, that use the strange, probabilistic, non-local mathematics of quantum mechanics to do things that nothing purely classical could do. The robin navigates by quantum physics. The compass led us here, to the edge of understanding, to the place where the needle points into genuinely unknown territory. There is a moment in the far north, in the winter, above the Arctic Circle, when the sky does something that no description quite prepares you for. The aurora borealis is familiar from photographs, but photographs do not move. The real aurora moves, it breathes, it ripples. It cascades in curtains of pale green and violet, and sometimes red, sweeping across the sky with a slow, sinuous, almost organic motion that looks like something alive. And it is, in a sense, alive. Or at least, it is the product of living processes, not biological life, but physical life. The ongoing, dynamic, responsive relationship between the sun's continuous exhalation and the Earth's magnetic shield. The aurora is what happens when charged particles from the solar wind, guided by the Earth's magnetic field lines toward the polar regions, collide with molecules of oxygen and nitrogen in the upper atmosphere. The oxygen glows green, mostly, at altitudes of around 100 to 150 kilometers. It glows red at higher altitudes, above 200 kilometers. Nitrogen glows blue and violet. The colors you see are the fingerprints of specific atoms, releasing specific wavelengths of light as electrons fall back to lower energy states after being excited by the collision with solar wind particles. The aurora is an emission spectrum, a rainbow produced not by water, but by air and magnetism and solar wind, and the particular quantum energy levels of oxygen and nitrogen atoms. The field lines that guide solar particles toward the poles are the same field lines that the compass needle aligns with. The compass and the aurora, the same geometry, the same invisible architecture. What the compass reads quietly, in the silence of a hand and a pivot and a glass housing, the aurora writes in light across the sky, as if the planet were not merely broadcasting its magnetic field as an invisible signal, but sometimes, on certain nights, when the solar wind is strong and the particles are numerous and energetic enough, writing it out where you can see it. Here, these are the field lines. This is the shape of the invisible thing I have been trying to show you. This is what north looks like, if you could only see it. The aurora is the compass made visible. The compass is the aurora made portable. Two expressions of the same planetary truth. One fills the sky. One fits in your pocket. Both are telling you the same thing. The field is there. The field is real. The field is holding you. And perhaps that is the deepest comfort the compass has to offer. Not direction, not navigation, not the practical, technical, instrumental value of knowing which way is north, but the knowledge, felt in the body, confirmed by the needle, that the field is there, that the planet is maintaining its shield, that the core is still churning, that the invisible architecture of the magnetosphere is still arching outward from the poles, still deflecting the solar wind, still protecting the thin film of atmosphere and ocean and life that clings to this particular rock, in this particular corner of an ordinary galaxy. The compass is not proof that you know where you are going. It is proof that the planet is still protecting you, that the mechanism is still running, that the Earth is still alive in its geological way, still warm in the deep, still moving, Still caring, if we can use that word loosely, for the continuation of everything that lives on its surface. The compass is not a reassurance about your destination. It is a reassurance about the ground you stand on. The field is there. The shield is up. The core is churning. You are held. The compass has a future. Not just as a backup navigation system for when GPS fails, not just as a survival tool, or a heritage artifact, or a piece of equipment kept in cockpits and navigation rooms more from tradition than necessity. The compass, the principle of magnetic sensing, of reading a field to determine direction and position, is being developed into technologies of extraordinary sophistication and subtlety. The quantum compass. Not the biological quantum compass of the robin's eye, though that is the inspiration. A human-built quantum compass. Several research groups, in universities and defense laboratories around the world, are developing magnetometers based on quantum effects, on the behavior of entangled particles, on the quantum properties of nitrogen vacancy centers in diamond, on the cold atom physics of Bose-Einstein condensates. These quantum magnetometers can measure magnetic fields with a sensitivity that dwarfs even the best conventional fluxgate magnetometers. Sensitivity measured not in nanotesla, but in femtotesla. A femtotesla is a millionth of a nanotesla, a quadrillionth of a Tesla. At these sensitivities, the instrument can detect not just the direction of the Earth's field, but the subtle, localized variations in the field caused by geological structures beneath the surface, or deposits, faults, archaeological features, the slight difference in magnetic susceptibility between disturbed soil and undisturbed soil that allows a magnetometer to detect buried foundations, old hearths, ancient ditches, without a single shovel being put in the ground. A quantum magnetometer, swept across a field, can see the buried past, can find walls that have not been walls for 2,000 years, can trace the outline of a forum, a temple, a house, beneath grass and time. The compass, in its most advanced form, sees backward, reads the past the same way paleomagnetism reads it, through the magnetic signals preserved in material that was once disturbed, once shaped, once made significant by human intention. The quantum compass will also navigate without GPS. This is the goal that is driving much of the research. GPS is extraordinary, but it is vulnerable. It can be jammed. It can be spoofed. It can fail in urban canyons where tall buildings block satellite signals. It fails underground. It fails underwater. A quantum inertial navigation system, combining quantum magnetometry with quantum accelerometry, measuring the Earth's magnetic field and the body's acceleration with quantum precision, could provide position information without any external signal. No satellites, no radio signals, no connection to any external infrastructure that could be disrupted. Just the field, just the Earth. Just the same planetary broadcast that the first Chinese navigators read with their floating lodestone spoons, now read by quantum physics with an accuracy of centimeters. The compass comes full circle, from the spoon of lodestone in the Han dynasty, through the dry compass of the medieval Mediterranean, through the precision instruments of the age of sail, through the gyroscopic and fluxgate compasses of the 20th century, to the quantum compass of the 21st. The same principle, refined by 2,000 years of human ingenuity, to a precision that the original compass makers could not have imagined, but the same relationship. The same basic, fundamental, ancient relationship between a sensitive instrument and the Earth's field. Listen to the planet. It will tell you where you are. There is another future for the compass that is quieter, less technological, more personal. There is a movement, small but growing, of people who are deliberately choosing to navigate with paper maps and magnetic compasses, not because they distrust GPS, not because they are survivalists or preppers, but because they want the experience, because they have discovered, or rediscovered, what it feels like to navigate with your whole attention engaged. to stand at a trail junction and look at a map, and look at the terrain, and take a bearing and think, to be genuinely uncertain for a moment, to figure it out, to arrive at a destination that you navigated to yourself, with your own skills, your own judgment, your own relationship with the instrument and the landscape. There is a satisfaction in this that is qualitatively different from following a blue dot. Not superior in every way. The blue dot is faster, more accurate, less cognitively demanding. But in the specific dimension of presence, of engagement with where you are, of relationship with the landscape, the paper map and compass experience is richer, more embodied, more real. And people who have discovered this are not letting it go. They are teaching their children to use compasses. They are taking orienteering courses and navigation workshops. They are going into landscapes without GPS, deliberately, in the way that some people cook from scratch rather than ordering delivery. Not because the scratch-cooked meal is necessarily better in every dimension, but because the act of making it is part of the nourishment. The compass will not disappear. The technology will advance. The physics will deepen. The applications will multiply. But the small, simple, handheld compass, the glass and the needle and the painted rose, and the trembling red end that always finds the same direction, this will persist. Because it is not only a tool, it is an experience. And the experience of holding something in your hand that knows which way is north, that knows it by listening to the planet, by the patient alignment of electrons, by the same force that writes light across the polar sky, that experience does not become obsolete. It becomes, if anything, more precious. Let us take one final, long, unhurried look at the compass. Not the idea of it, not the history or the physics or the philosophy, the object itself. A compass. Perhaps it is old. Perhaps it belongs to your grandfather, sitting in the back of a drawer, its brass case green with oxidation, its glass slightly clouded, its pivot still good, the needle still active. You take it out. You hold it in your palm. Level. You wait. The needle swings. It oscillates. Back and forth, back and forth. Each swing slightly smaller than the last. The dampening fluid dissipating the energy. The mathematics of friction and momentum playing out in the tiny enclosed world of the compass housing. And then, it stills. The needle rests. One end pointing. And this is the part that never quite loses its power, no matter how many times you do it. One end pointing in a specific direction. That direction is connected to the center of the Earth, to the liquid iron that is, at this moment, thousands of kilometers beneath you, churning in currents driven by heat as old as the solar system. That direction is connected to every ship that has ever crossed an ocean, to every navigator who has ever stood on a rolling deck, in the dark, in the cold, checking the bearing, holding the course, to every bird that has ever oriented itself in the vast, featureless Pacific, to every bacterium that has ever spiraled down through ocean water toward oxygen-poor sediment, following the dip of the field, to the ancient rock that recorded the reversal that happened 800,000 years ago, to the explorer in his army camp, writing his letter about the magnet, astonished by its behavior, reaching for the language to describe something he could feel, but not explain. The needle is pointing, and it is pointing at all of this, all at once, in one small, still, trembling gesture. There is a thought I want to leave you with before we reach the end. The Earth's magnetic field, the thing the compass reads, the thing it has always read, is what physicists call a dipole field. It has two poles, two ends, two directions. And between those two poles, the field lines curve outward in great arcs, reaching into space, then returning, completing the loop. The field is not a one-way street. It is a circuit. It goes out and comes back. It leaves the South Pole, arcs through space, returns to the North Pole, travels through the Earth, returns to the South Pole, endlessly. without pause. A closed loop of magnetic force that has been running for billions of years. And here is the thing about closed loops. There is no beginning. There is no end. You can trace a field line from south to north, from north to south, from the surface into space, from space back to the surface. You can follow it all the way around and arrive back where you started. It is a circle, a perfect, elegant, invisible circle drawn around the planet. And the compass needle, aligned with one segment of that circle, feeling the field in its tiny, local, immediate way. The compass needle is pointing along a line that goes all the way around the world, back to where you are, back to you. North is not a way. North is a direction that, if you follow it far enough, brings you home. Every compass bearing, in the end, is a circle. Every direction, followed to its conclusion, completes the loop. You can go out and still come back. The field will be there when you return. The needle will point you home. The compass has taken us far, through the liquid iron heart of the planet, through the magnetotactic bacteria spiraling in ocean sediment, through the eye of a robin, where quantum physics performs its impossible intimate magic, through the holds of ships crossing unknown oceans, through the stripes on the ocean floor that told us the ground beneath our feet is in motion, through cave systems and iron cycles and solar storms and the aurora borealis, through the philosophical weight of a needle that points without choosing, through the medical instruments that read the body's own magnetic whisper, through the art and literature and music and thought that the compass has inspired, through the futures being built on quantum sensing, on the most sensitive listening the human mind has yet devised. We have been far. And yet the compass itself has never moved. It sits in your hand. It points. Outside, right now, wherever you are, whatever the season, whatever the weather, the Earth's magnetic field is present. You cannot feel it. Your skin has no magnetoreceptors. Your nervous system, as far as we know, has no conscious access to the signal that the robin reads so fluently. But the field is there, arching over you, surrounding you, threading through the walls of whatever building you are in, if you are inside, through the ground beneath you, through the air above you. At this latitude, the field has a specific intensity, a specific declination, the angle between magnetic north and true north, which someone has calculated and published and updated every 5 years because the pole has moved slightly since the last calculation. A specific inclination, the angle at which the field dips into the Earth, which is different here than it is at the equator, different than it is at the poles. Your location has a magnetic signature, unique to you, right now. The field is always specific, always particular, always here. And if you held a compass, if you slid it out of a case and held it level in your palm and waited for the needle to still, it would tell you. It would tell you which way north is, not north in general, north from here, north from exactly where you are, in this moment, on this spinning, breathing, field-maintaining, life-protecting planet, north from you. The compass does not judge where you are. It does not compare your location to other locations and find it wanting. It does not ask whether you should be somewhere else. It simply orients you to where you are, gives you a bearing, gives you a reference. Here is north. Now you know where you stand. And knowing where you stand is, in the quietest possible way, one of the most profound things a person can know. Not in the geographical sense alone. In the existential sense, I am here. This is the direction I am facing. These are the directions available to me. The compass does not tell you which direction to go. It only tells you what directions exist. It gives you the full rows of possibilities, north, south, east, west, and every compass point between. And it tells you which one is which. The rest is yours. The rest has always been yours. And so the compass, having navigated the seas and the centuries and the caves and the bodies and the quantum frontier, comes to rest here, in your hand, in this moment, pointing north. Not because of magnets and needles and physics, though it is all of those things. Not because of the brave and the brilliant and the lost and the found, though it has been part of all of those stories. It points north, because the Earth is alive, because the core is still churning, because the electrons in the iron of the needle are still, at this very moment, aligned with the field, still listening, still in agreement, still doing the only thing that magnetized iron in contact with a planetary field can do, still pointing. Close your eyes for a moment, not to sleep, just to feel it. The weight of the planet beneath you, the 4.5 billion years of it, the iron at the center, and the rock above, and the ocean, and the atmosphere, and the magnetosphere arching overhead. The field, running through everything, through the rock you are sitting on, through the building, through your body, through the space above the city or the forest, or the sea. The field, that has been running since before there was anything alive to notice it. That ran through the first rains that fell on the early Earth. That ran through the first ocean. That was there when the first bacterium built its chain of magnetite crystals and felt the dip of the field and followed it downward into the sediment. That was there when the first bird spread its wings and felt the inclination of the field through the cryptochrome in its eye and knew which way south was and went. That was there when the first human hand picked up the first piece of lodestone and felt the strange, impossible pull of iron against stone. That is there now, holding, orienting, protecting, whispering its ancient, wordless, electromagnetic signal into everything that is sensitive enough to hear. This way, this way, this way. Somewhere right now, a ship is crossing an ocean. At its helm, a compass, the needle pointing. Somewhere right now, a team of scientists is lowering instruments into a borehole drilled into ancient rock, reading the magnetic record of a world that has not existed for 3 billion years. Somewhere, a child is holding a compass for the first time, both hands, very level, watching the needles swing and settle. Somewhere, an Arctic tern is crossing the equator, 100 meters above the South Atlantic, its cryptochrome eyes reading the field, its body navigating by quantum physics it will never know it is using. Somewhere, magnetotactic bacteria are spiraling through the sediment of a quiet estuary, each one carrying its tiny chain of magnetite crystals, each one tuned to the Earth's oldest signal. Somewhere, in the deepest part of the outer core, liquid iron is moving, slowly, massively, in currents that take decades to complete a single circuit, generating the field that holds everything, that has always held everything, that will hold everything for billions of years to come. And in your hand, if you chose to hold one, the needle, the small, still, trembling needle, listening to all of it, connecting you, through the simplest possible instrument, to the deepest possible thing, the heart of the planet, the circuit of the field, the arc of the aurora, the path of the bird, the memory in the rock, the quantum whisper in the eye, all of it. The compass points north, and north is everything. Rest now. You know where you are. The field is there. The needle is still. And the Earth, as it always has, is holding you.